Okay, so page 30 and looking at our reacting amount calculation. So you would have done this at GCSE and it's a style of question that would ask you, they would give you a certain mass of something and ask you to work out, well, either what is the mass of a reactant that I would need to produce this amount, or what is the mass of product that would be formed from this amount of a substance. And it really stems from the fact that we can read a balance symbol equation quantitatively. That's why at GCSE your topic would have been called quantitative chemistry. So if I even remind you of a really simple equation that you would have looked at GCSE, the reaction of magnesium reacting with oxygen. So that balance symbol equation would be 2Mg plus O2 giving you 2MgO. And that equation we can read quantitatively. We can read that as 2 moles of magnesium would react with 1 mole of oxygen to produce 2 moles of magnesium oxide. But we don't always have a specific number of moles. We don't always have 2 moles of magnesium. It's really just the ratio. These balancing numbers tell us the ratio in which our reactants react together and our products are formed. So it could be something like, say for example, we had 4 moles of magnesium. That means that would react with 2 moles of oxygen to give 4 moles of magnesium oxide. It's just a ratio. So that's why when we look at the steps for these calculations, if you're not given an equation, you need to make sure that you write a balance symbol equation and make sure it's balanced correctly, because these balancing number ratios will be really, really important in these calculations. Okay, so we can read an equation quantitatively, but the amount of the substance that we have must be in moles and not in mass. So if you're given the mass of a substance, you can't just bring it anywhere else in the equation. You've got to transfer your number of moles. Okay, so how this question is likely to be given to you is you're given a mass of a substance, you need to convert that to moles and then bring it elsewhere in the equation, just factoring in your ratio as well. So if I bring these steps back up, okay, number 1, write an equation for the reaction and make sure it's balanced. What I would then do is write the information I know, the information I've been given in the question, underneath the equation, including the RFM of the substances that you're going to be working with, and we'll see that in a worked example. What you'll then need to do is the mass that you've been given, you'll need to convert it to moles just by your equation, N equals mass over RFM, or moles equals mass over molar mass, whatever you're used to using. Then number 4, you might not be familiar with this term that comes at the end of this. It says transfer to the substance in question, the one you're asked to work out, by multiplying by the stoichiometric ratio. If you haven't heard of that term, it's just a balancing number ratio. So if we were going, say, from magnesium to oxygen in this, it would be 2 to 1. It's the same as your balancing number ratio. So if you're not familiar with that term, stoichiometric ratio, don't worry. It just means the balancing numbers ratio. And then once we've brought our moles over to the substance that we're trying to work out the mass of, we just simply convert to mass by using mass equals N times RFM. Okay, so the key thing to remember with these is make sure you remember your balancing number ratio, but also that you can only move moles. You cannot move masses. Okay, and so let's go over the page and we'll try an example of that. We'll try worked example 1. Okay, so this is page 31 and we'll look at worked example 1. So it says here, calculate the mass of magnesium chloride formed from the reaction of 4.8 grams of magnesium with hydrochloric acid. Now, if you're only given the mass of one thing, you just assume that you work with that and not anything else. We will do in our next lesson something called limiting reactant calculations that you would have done at GCSE. Sometimes you're given the mass of 2 reactants and you need to work out what's your limiting reactant before moving on. But here we're just given one bit of information, so that's what we have to work with. We can assume that the hydrochloric acid is in excess. So what I want to do is go through the question again and then write down the information that I've been given underneath the equation. So it says here, calculate the mass of magnesium chloride. So that's what I want to work out. So underneath my magnesium chloride, which is MgCl2, I would write question mark mass. That's what I've been asked to work out. What is the mass? So I would write that underneath. Formed from the reaction of 4.8 grams of magnesium So that's another bit of information I've been given, and I would write that underneath the relevant part of the equation. This time the equation's been given to you, so you don't have to write it, okay, but you may be asked to write the equation as well. So these are the two things that I'm going to be working with. So these are the two things that I'll need the RFM of, because when I'm working out the number of moles, I need the RFM for my equation, and then when I convert that back to mass, I'll need the RFM of this thing. So I'd encourage you to work this out at this stage of the equation so that you're not fumbling around by the time you get halfway through your calculation working out your RFM. So if we have a look at your periodic table, and if you haven't got your periodic table out, I would encourage you to do that because you'll need that for later on today anyway. Okay, if you find magnesium on the periodic table, it's just one atom of magnesium. So that's just going to be its relative atomic mass, which is 24. Okay. For magnesium chloride, you can do a little bit of working out here. It'll be 24 from your magnesium plus 2 times your 35.5 from your chlorine, and that should come out then as 95. So it's worthwhile working out those RFMs at this stage so that you're ready to use them in your equations later. You don't need to worry about hydrochloric acid or hydrogen because we're not going to use them in this calculation. Okay, so we always start with the information that we've been given, the substance where we've been given its mass, because right now we can't use any equations with magnesium chloride. We can only use it for magnesium. So we'll use our equation, N equals mass over RFM, to convert to your number of moles. So that's going to be 4.8 divided by 24. And you can do this in your calculator along with me if you have your calculator out. Okay, but that comes out as 0.2 moles, 0.2 MOL. Okay, so what I want to do is I now want to take that number of moles over to magnesium chloride, what I've been asked to work out the mass of. So I bring that over, and I might set these out a wee bit differently than you did at GCSE. So if you want to set it out the way you've been used to, that's fine. But I just usually take my number of moles and use an arrow, and then I always write my ratio on the arrow. What is the ratio of magnesium to magnesium chloride? 1:1, perfect, okay. So here we don't really need to do anything because however many moles of magnesium we have will produce the same number of moles of magnesium chloride. That's in an ideal world. These calculations assume that our reactants are completely 100% efficiently changed to products, and that's not always the case, but these calculations assume that. So that means I'm going to produce 0.2 moles of magnesium chloride. But I haven't been asked to work out the number of moles, I've been asked to work out the mass. So at this stage, just one final step of the calculation. I use the rearrangement of my mass and moles equation to mass equals N times RFM. My number of moles is 0.2 and the RFM is 95. You can see how it's handy to have that worked out already. And that should come out in your calculator as 19, and then the units are grams. So remember, when you use these equations, mass is in grams, so make sure to put your unit at the end. If it turns out to be a really big number, which we'll see in one of our later examples, you can convert it back to kilograms or tons, but as it comes out is in grams. Okay, so just to go through work example 2 then, again, go through your questions, see what you're being asked to do and what information you've been given, and I would encourage you to write that underneath the equation. So here you've been told 5 grams of calcium carbonate, so I would write that underneath my calcium carbonate, and then I'll need to work out the RFM of that. I'll do that in a second. It's heated to constant mass. What mass of calcium oxide is obtained? So it's important that you know what they're asking you for. So that is calcium oxide, so I put my question mark mass underneath that. Okay, I'll need my RFM of that as well, and I can essentially just ignore carbon dioxide. So hopefully you worked out your RFM of calcium oxide as 100, or sorry, calcium carbonate as 100, and then calcium oxide as 56. Okay, and then converting to moles first of all with what you've been given. N equals mass over RFM. That's 5 over 100, which is 0.05 moles. Again, hopefully you saw that your ratio is simply 1 to 1. So 0.5 moles of calcium oxide is going to give you 0.05 moles. Sorry, I think I'm saying this the wrong way around. 0.05 moles of calcium carbonate is going to give you 0.05 moles of calcium oxide. Then just convert simply back to mass by using N equals moles times RFM. And then that's 0.05 times by your 56. And that will give you 2.8 grams. And let's have a wee look at worked example 3. There's a couple of things to look out for in worked example 3. Our ratio this time is not 1 to 1, so we'll need to have a think about that. And we also need to have a think about our unit. So again, just go through the question, write the information that you've been given underneath the equation. So it says, in the blast furnace, hematite Fe2O3 is converted to iron, something that you studied at GCSE. It says, what mass of iron, so that's my question mark, can be obtained. So it's a product. And you can see that it's there on the right hand side. We can write our question mark mass there. Can be obtained from 16 tonnes of iron oxide. So underneath your iron oxide, I would write 16 tonnes. Okay, and then you're ready to proceed with your calculation. Again, I'd encourage you to work out your RFM first. So your RFM of iron oxide, find it on the periodic table. You have 2 irons and 3 oxygens. Okay. So that's going to be 2 times by 56 plus 3 times 16. And hopefully that comes out as 160. Okay. And then your irons, just be careful when you're working out your RFM. Don't include the balancing number when you're working out the RFM. Remember, the relative formula mass is the relative mass of one formula, so that will just be of Fe. That balancing number there is part of the whole overall equation. It's not part of the formula of iron itself. We take that too into account when we do our ratio, our balancing number ratio later in the calculation. So don't include it at the RFM stage, because then you end up multiplying by 2 twice, and that will get you the wrong answer. So the RFM of iron is just of Fe, which is 56. So ignore balancing numbers when you're doing your RFM. Okay. So then what we need to be careful of before we do our calculation with iron oxide, anything you spot that we need to do? Good, convert it to grams. How many grams is 16 tonnes? Yeah, good, 16 million grams. Okay, so when we use our moles equation, we must have the mass in grams. Okay, so at this stage, we're ready to do N equals mass over RFM. That's going to be 16 million over our RFM of 160. And that should come out as 100,000 moles. Okay. So this is the number of moles I'm transferring over to iron, but I need to be careful about my ratio. What is the ratio here? 1 to 2, okay? If there's no balancing number in front of a formula, that means it's just essentially 1. So it's 1 to 2. What does that mean I need to do? Good, I need to times my number of moles by 2. Essentially, when you're working, sometimes the ratio can be harder than that. It could be like, say, 3 to 2. And you're essentially dividing by your first number. So I'm essentially dividing by 1, timesing by 2. So in this case, essentially, I'm just timesing by 2. And that's going to give me 200,000 moles. From that point, I'm ready to convert back to mass. And just do mass equals N times RFM. So that's going to be 200,000 times by 56. Okay, and that should come out as 11,200,000 grams. That's obviously quite a large value. So at this point, I would probably convert that back to tonnes or even kilograms. So to convert back to tonnes, you'd be dividing by 1,000,000, and that would then come out as 11.2 tonnes. Okay, just because it's quite a big answer. Just be just be careful, look out in the question, have they specified what unit they want it in, but generally try and quote your answer in the same unit as the question, as it's given in the question. So you're told you have 16 tonnes of iron oxide, so try and make your answer in tonnes as well. If they don't specify, it doesn't matter, but that's probably the best way to do it. So just be careful if, to double check your ratio. Here it was 1 to 2, and we needed to take that into consideration, otherwise your answer would be wrong. Okay, we'll do one more worked example here, and I'm aware this should be really worked example 4 rather than worked example 5, so you can change that if you wish. Okay, and this worked example is just reminding you that once you've got the number of moles of the thing that they've given you the information of, whenever you've got the moles of one thing in your equation, you can move it anywhere else in the equation as long as you're moving the number of moles and as long as you take into consideration your ratio. Okay, so sometimes they will give you the mass of a product and ask you for the mass of the reactant that you would need to produce that amount of a product. Okay, so if you know you want a certain amount of product, working backwards to work out how much reactant you would need. And this is a really common calculation that industrial chemists will use. If they know they need to produce a certain yield of something, they need to work out how much of their reactant to react together. Okay. And so here in this question, sounds like a biology question. You're told a bit of background information there in the question. That's really just to build your equation. But the last part of the question says, calculate the mass of glucose required. So calculate the mass of glucose required. So that even that word required tells you that this is a reactant I'm being asked for here. So the mass of the mass of glucose required. So I'm going to put my question mark mass underneath glucose. If you're not sure the formula of glucose, well, you're just identifying it from this equation, and hopefully you know that O2 is oxygen, so the other thing must be your glucose. And that's required to produce 432 grams of water. So I'll write that underneath my water. Again, I'll need my RFM of these things. So if you work out the RFM of glucose with 6 carbons, 12 hydrogens, 6 oxygens, it comes out as 180. The RFM of water then, remember it's of just one unit of water, so one formula of H2O, and that's 18. So remember, don't include your balancing number at this point. You can do that later. You'll do that later on with your ratio. Okay, so this time it's a bit different. I'm starting over on the right-hand side because that's what I've been given the mass of. So that's N equals mass over RFM. So the mass is 432 divided by your RFM. And that should come out as 24 moles if you're doing this in your calculator along with me. Okay, that is the number of moles I will then transfer. I want to produce 24 moles of water, so how many moles of glucose do I need? What is my ratio here? Yeah, good. It's 6 to 1. Now, different people will set this out different ways. Sometimes people will write on the arrow 1 to 6 to kind of keep the numbers consistent with the way they're arranged in the equation. I actually prefer to just think, well, in the direction I'm going, it's from 6 to 1. And so therefore, that's what I'll write on the arrow. And it kind of keeps it consistent in what you're doing. So what are you doing this time? Are you dividing by 6 or multiplying by 6? Good, you're dividing by. And that keeps it consistent. You're dividing by the first number, multiplying by the second number in your ratio. So that's 6 to 1. Divided by 6 times by 1. So how many moles of glucose will you need? 4, good. And then just the same as always, convert back to your mass by doing mass equals N times RFM. That's going to be 4 times by your 180. And that should come out as 720. And then put a unit at the end. Always remember, mass must have a unit, and to put that in your final answer.